So, Dr. Godes,
Hey Tyler.
how was the ice?
Ice was pretty good. It was pretty good. But I did want to go over another example of it,
Okay.
right? Practice makes perfect. And so we have our friend here, the sulfur trioxide reacting to form sulfur dioxide and oxygen.
Looks familiar.
Right, and so imagine you want to know what K is, and you do an experiment where you put 0.02 molar sulfur trioxide in a flask. And you seal it up, and then you wait for it to react. And it kind of reacts, it's a little slow, so you go and have some coffee, you come back.
Alright, is it done now?
Yeah, I think it's done.
Great.
And then to measure the equilibrium constant, you want to know how much of each compound is there left. Well, you could weigh the flask, but that would tell you that the mass has not changed because conservation of mass. Right? And some things are easier to measure than others, and so maybe you have an oxygen probe, a probe that measures just oxygen. We have a bunch of those in the lab. And you stick it in there, and you find out that the oxygen concentration is 0.0029.
Alright.
And so what that means is that we know that at equilibrium, the oxygen concentration is 0.0029. Okay, so by making that one measurement, we know what X is. We can actually substitute all of the X's in all of this now, right? Because X is tied to the other ones by stoichiometry.
Great.
Okay, so what's this going to be?
That would be 0.0058.
0.0058. And a molar, I'm going to leave that off there because I'm running out of room. And I could substitute that in there too. And now to calculate K, well, all I do is substitute in here.
Right, let's substitute with our little substitutors.
Okay.
Great substitution.
Yes, like magic. And then just plug it into the calculator, right? We calculate that out, and what we find is that I got a value of 4.8 times 10 to the minus 4 for that. And again, no units on equilibrium constants, no units. Okay, so once you set up the ice table correctly, you just have to identify, what does the problem tell me? Does it tell me a change? Does it tell me a final concentration?
Right.
But you have to pretty much fill in what it tells you. Don't assume that it's going to give you the same thing that the last problem gave you, because it might be very different.
Alright.
Okay, I did want to mention one other piece,
Okay.
and we'll have to go over to the other board.
Alright. So this is the second piece?
Yeah, it's the second piece, but really it's the first piece. It's the first thing that you guys did. And it was about reactions that happen in a series. Right? And so here we have two reactions. A plus B goes to C, and I should probably make these equilibrium reactions since they're K's. And two C's go to D. And if these two reactions happen in series, well, the overall equilibrium constant is related to the equilibrium constants of the steps.
There you go.
Right? But before I add together the steps, I better make sure that it kind of makes sense, right? So what do I mean? I mean, the second reaction, there's two C's here. I only made one up there. And so if I want kind of a balanced reaction that makes sense, I better make two C's up in this first step.
Right.
So how do I do that?
Well, you can just multiply the whole reaction by 2.
Yeah, I multiply the whole reaction by 2.
Now you have 2 A's, 2 B's, and 2 C's.
And 2 C's. What do I do to the equilibrium constant when I multiply the reaction by 2?
Could you multiply it also?
You could multiply it also, but let's think about the equilibrium constant, right? What does it mean when I put a 2 there? I could distribute that 2 throughout, right? I could say 2 A's and 2 B's and 2 C's, and when this goes into the equilibrium constant, or the equilibrium expression, what do I have to do to the concentration of C? Do I double it?
No, wait a minute, you square it.
Square it.
You square it.
Exactly. So when I double the reaction, I have to square the equilibrium constant. Now when I add these two reactions together to get the overall reaction, well, the two C's are going to cancel out, and I end up with 2A plus 2B goes to D. And now I have K3. Well, how do I combine these two to get K3? I added the reactions together.
But you can't do that. You should multiply.
Multiply, right? You end up K3, the equilibrium constant for that final one, you take this one times that one. So K1 squared times K2.
Ah.
Right, and this turns out to be a pretty useful thing sometimes in chemistry, because a lot of times in tables you'll see reactions that are commonly happen in individual steps, and you want to know, well, what's the overall reaction? Is it going to go to products? Is it going to be reactants? And so this is how you do it. What if I flipped one of these backwards?
Well, then it wouldn't work because they don't cancel when you add them together.
Yeah, and so you'd have to flip it, and when you flip a reaction backwards, the equilibrium constant, you take the reciprocal, the inverse of it.
Right.
So those are kind of the manipulations you need to remember when you're adding reactions together in a series.
All right.
All right?